you are welcome to the second part of part 2 of projectile. We have explained projectile in one dimension. We give the definition of projectile, the definition of trajectory of a projectile, application of projectile in warfare, in sports, and we look at examples under upward motion. Upward motion. Today we want to look at this is the continuation, downward motion. Downward motion. Let's see examples under downward motion. Let's look at downward motion. So you know the meaning when you have, let's say this is the ground, this is a building, for example, or a cliff. So the body is now thrown vertically downward like that. It's thrown vertically to have time, height. We have the height here, and you have the time taken to reach the foot of the cliff. So under downward motion, when a body is thrown vertically downward. When a body is thrown vertically downward, such a body has the following. As following parameters. The following parameters, namely parameter 1a, its final velocity is never equals to 0 meter per second. B, initial velocity is equals to 0 meter per second. C, S, distance, and we will see S, distance covered is equal to height of projection. D, then you take your A to be equals to G plus G. These are the parameters for upward motion. Let me remind you for downward motion. Let me remind you under upward motion, I said V is equals to 0 meter per second at maximum height. Still remember, while U is never equals to 0 meter per second, but maximum is never equal to 0. Our A is equals to minus G, and S still remain H. These are the parameters for upward motion. The downward motion, these are the parameters. So we want to find the time taken for a body projected vertically downward from the top of a building, the time you take to reach the foot. Then we want to calculate the height. These are the two things we want to determine. And the height, the time. Let's look at time taken. Time taken to reach the plane of projection. Plane of projection. Time taken to reach the plane of projection. Many time taken to reach the foot of the building, the foot of the cliff. That is what we are trying to say here. So small t, you know, from V is equals to U plus 80. V is equals to is never equal to 0, as we have rightly said. U is equal to 0 meter per second, and A is equals to plus G. So this one will be V is equal to 0 plus GT. So you have V is equals to GT, and T is equals to V all over G. This is the first formula. This is the time taken. We have V is equals to final velocity. What of the height of projection? Maximum height of projection, you can say height of the building, height of the building, height of the cliff, height of any. So that is the height. So from S is equals to UT plus half AT squared. This one will turn to H. Initial velocity is 0 for downward motion plus half GT squared. Anyway, you see you put G. H9 is equals to half GT squared. This is the formula for finding the height of projection, the height of the building, and etc. So let's go back to time. There are two formulas you need to take note, V over G. There's another formula by making G the subject of the formula, T the subject of the formula here. So from H is equals to half GT squared. So I can say that GT squared is equals to 2H. T squared now is equals to 2H all over G. T now is equal to square root of 2H all over G. This is another formula for finding. This formula is very, very important. Square root of 2H over G for calculating the time to reach the plane of projection for a body projected vertically downward. So please take note of this formula, and this formula. Let me call it velocity time graph. Velocity time graph for downward motion. Velocity time graph for downward motion. So if velocity is plotted against time, V in meter per second, and time is seconds. So in this case, you are going to have this is the graph, velocity time graph. Remember, this one is for downward. Let me remind you, this is for downward motion. Let me remind you for upward motion. We have done that one. It's like this. Still remember, velocity here in meter per second, time in seconds. In our first video, we have explained this. This is upward motion, velocity time graph for upward motion. But that is graph 1. Another graph is a graph of height against the graph of height h against t squared for downward motion too. For downward motion, recall that we have established that h is equal to half gt squared. Clearly, h direct proportional to t squared. H direct proportional to t squared. So if you want to plot this graph, you have the graph here. You have h in meter times t squared in second square. So when you plot the graph, it's a direct variation. So it's a straight line graph. And why is the graph? Another one is they will now ask you to plot the graph of h against in meter against time in seconds. You can see the difference. T squared, h against t squared, and h. Each time they ask you to draw this, they will equally ask you to draw the h in meters against this. So this one is this is the graph of h against t. This is the graph of h against t squared for downward motion. Please take note of that. So let's look for example 1. Example 1. A particle is projected. A particle is projected vertically downward from the top of a cliff, 80 meters high. Calculate the time taken to reach the foot of the cliff. Full stop. Take G to be equal to 10 meter per second square. That's all. In this question, what are the parameters given? You are given height, 80 meter. G is given to be that, 10 meter per second square. Then calculate the time. So far it is downward motion. Time is either V all over G or T is equals to square root of 2h over G. So far we are not given velocity. So I'm using this 2h all over G. So T will now be square root of 2h over G. This will be 2 times 80. So divided by 10. Cancelled. You have square root of 16. So this one will give you 4. That is 4 seconds. Example 2. The time taken by a body projected vertically downward to reach the foot of a cliff. The time taken by a body projected vertically downward, yes, from the top of a cliff to reach the foot of a cliff, vertically downward to reach the foot of a cliff is let's say 2 seconds. Calculate the height of the cliff. Also, determine the velocity with which the body strikes the foot of the cliff. That's the question. So in this question, what you need to do is you are given time to be 2 seconds. The first one has to calculate the height, and again you have to calculate velocity. That's, definitely is final velocity. So h is equals to half gt squared. H is equals to half times 10 times 2 squared. H is equals to 5 times 4. H9 is equals to 20 meters. So the height is 20 meters. It's 20 meters of the cliff. The velocity we call also T is equals to V all over G. Clearly V is equals to GT. G taken to be 10. Time is 2. So the answer is 20 meter per second. Horizontal motion. If you look at the classification again, as a projectile divided into two, in 1 dimension and 2 dimension. In 1 dimension is subdivided into 2 as well. We have vertical motion and horizontal motion. Vertical motion, upward motion, and downward motion. So we want to look at horizontal motion. This is more or less the same thing as a downward motion. It's more or less the same thing as downward motion. There's a difference between when something is dropped downward like this and is thrown like this horizontally. It's thrown like this. Definitely it will cover. This is the point of projection. This is the point of landing. So we want to get the range is here. This is what we call horizontal distance. Call it horizontal distance. Horizontal distance. So this is the height and this is the time. You can see this is still the same thing as a downward motion. For downward motion, height still remain half gt square. We use it for horizontal motion. The two formula are this formula. Then time also, remember, is square root of 2h all over g. It's applicable for downward motion and horizontal motion. What we want to derive here is the range. So what is the meaning of the range? The range of projectile. This is the horizontal distance. Horizontal distance covered by a particle projected. This is the horizontal distance covered by a particle projected from the point of projection, to the point, this is the point of projection, to the point of landing, Please take note of the definition. Is the horizontal distance from the point of projection to the point of landing. That is the range. It's a distance. So how do we derive the formula for the range? Can come here to derive the formula. You know, A for downward is plus G. A for upward is minus G. But A for horizontal, it has no horizontal component. So under range, A is equals to G, then plus is equals to 0 meter per second, because 0 meter per second square, because we are dealing with horizontal distance, and it's very, very important. Take note of this. So from S is equals to UT plus half AT square. This S we turn to that the distance range. UT, we leave it, half GT square. A is G. So R9 is equals to UT plus half. I've told you, horizontal component of G is equal to 0. So 0 times T square. So R9 is equals to UT plus 0. Everything of 0. R9 is equals to UT. This is the formula for finding the range on one dimension, in one-dimensional projectile. So another formula, recall that T is equal to square root of 2h over G. You can replace it and put R is equal to square root of, you have U here, then T is 2h all over G. This is another formula for finding the range. It's either you use UT or U square root of 2h over G.